we're delighted to have a talk today from Dr. Sathsara Abeysinghe from Cardiff University. Just as a brief introduction, so Sathsara is a postdoctoral research associate at the Centre for Integrated Renewable Energy Generation and Supply at Cardiff University. Her research interest includes statistical assessment of energy distribution networks, flexibility provision from decentralized resources, and operation improvement of local multi-vector energy systems. And today she's going to be talking about her SESI FlexFirm project. So without further ado, I'll pass over to Sathsara.
Okay, thank you, Man. Can you confirm if you can hear me well?
Yeah, we can hear you,
Okay,
well.
Okay, thank you. Thank you for inviting me. So good morning, everyone. Today I'm going to talk about a decision tool for real-time operation of public sector multi-energy systems. And at the beginning, I want to say that this is an ongoing research project at Cardiff University. And I'm working with several other colleagues on this research project, including Dr. Mudita Abeysinghe, Alexandra Canet, Professor Nick Jenkins, and Professor Jianzong Wu. So this is the outline of my talk today. First, I will introduce you to the partners of this project, and then I will give a bit of background on the net zero challenge and what it means for the public sector. Then I'll give an introduction to the public sector multi-energy systems. Then I will go on and describe the development process of the proposed decision tool in 3 key steps. And finally, I will show you the case study and the results. So to give you a bit of information on how this research started, so we were awarded 2 research grants through the National Centre for Energy Systems Integration, SESI, to develop a decision support tool that can translate the academic research in this area to a functional tool that can be used in the practical applications to improve the operation of public sector energy systems. So in the phase 1 project, we managed to quantify the potential benefits that can be achieved through optimal operation of public sector energy systems through 2 case studies. And in the current phase 2 project, we are developing decision tool to realize these benefits in the practical world. So this slide shows you all the partners who supported and involved in this project. And moving on, to give a bit of background as to why we need such tools to improve the operation of public sector energy systems. As we all know, UK is the first major economy to pass laws to bring all greenhouse gas emissions to net zero by 2050. So it is also important to note that in many ways, UK government expect the public sector to lead the decarbonisation agenda. So different public sector organizations have committed to voluntary targets. For example, as the largest public sector organization, NHS has committed to a voluntary target of 50% greenhouse gas emissions reduction target by 2025 and net zero by 2050. So what is this public sector? So the government estate is made up of large number of assets, including hospitals, schools, prison complexes, and many more. And this public sector consumes about 6% of UK's energy supply. And also it accounts for about £2 billion per annum for the energy bills. So it is also important to note that these public sector organizations are typically very large users of electricity and heat, and they usually own and operate their own on-site energy systems. So this figure shows you 2 examples of campus-scale energy systems in 2 public sector sites, which we are using as the case study sites for our research project. So the left-hand side figure shows a simplified schematic of the energy supply system of Queen Elizabeth Hospital, King's Lynn, and on the right-hand side is the simplified diagram of the University of Warwick campus energy system. So as you can see, there are different energy vectors such as electricity, gas, heating and cooling, and also some technologies connecting to the individual energy vectors such as the wind turbines, solar farms, and also there are some other technologies such as the CHP, combined heat and power generators, that combines multiple energy vectors together. For example, the combined heat and power generators consumes the gas and produces both heat and electricity to supply to the on-site electricity and heat demands. So before moving on to describe or discuss how we build decision tools to improve the operation of public sector energy systems, I think we need to first understand the challenges in the public sector energy systems, and specifically by the challenges faced by the energy managers on these sites. So the common challenges include the energy system being one of the main priorities in the normal day-to-day job, and also the system resilience is more important than the efficiency. For example, if you think about a hospital site, which is a very critical infrastructure, the resilience is much more efficient than the efficiency. And also most of these infrastructure or the equipment are very old, and also there are financial constraints and lack of engagement with the energy system, and also lack of investment. And we also identified lack of an energy strategy. Apart from these common challenges, there are also some other technical challenges we need to keep in mind. For example, carbon savings not more aligned with this gas CHPs, considering that the grid carbon intensity is being reduced with a lot of new renewable generators connecting to the electricity grid. The use of CHP to generate electricity on site is becoming not very carbon efficient. And also plethora of low carbon technology options coming into the picture. So a lot of energy managers are under the pressure of managing these new low carbon technologies on their energy systems. And also there is a reluctance of the designers and contractors to deviate from traditional technologies. And also there are local DNO constraints, like because of the grid constraints for additional PV or wind generation to be connected. Sometimes there are export constraints added to these on-site energy systems. And also complexities and uncertainties in the energy sector delay decisions. So having understood all these challenges, now let's look at how complex is this problem of optimizing the operation of an on-site energy system of a public sector site. So this slide here shows the factors that impacts the operation of a typical public sector or campus type energy system. So as you can see, there are price fluctuations for electricity and gas, and also need to manage the grid constraints. And also there are weather variations. If there are renewable plants like wind or solar PV, these weather conditions matter, and also weather conditions matter for the energy consumptions. And also if there are energy storage devices like thermal storage and battery storage, that makes the optimization even more complex. And also if there are on-site energy conversion technologies like the CHP, then their operation schedule, all that depends on these kind of factors. However, if you look at how the current energy management systems operate, actually they are based on very simple static rule sets, primarily to supply the on-site electricity demand and also to supply the heat demand. So mostly it is more about supplying the heat demand by the CHP generators and the gas boilers, and the remaining electricity demand being imported from the grid. So having understood these complexities, now let's look at how we are proposing a development of a decision tool uh, to improve the operation of the public sector energy systems. So this development process is done in 3 key steps. So the first step is to do mathematical modeling to quantify the potential cost, carbon, and energy saving opportunities of these energy systems. So this was actually done in the SESI Stage 1 project. And having understood and quantifying these benefits in the SESI Stage 2 project, we are moving on to implementing these benefits in the real system. So in order to do that, we proposed 2 key steps. The second step is very important, that is about establishing digital twins of these campus type multi-energy systems to do the testing of the new control strategies. So like I said before, most of these campus energy systems are critical infrastructures like the hospitals and universities, so you cannot really interrupt their operation to test the new controls. So that's one of the main reasons we went for implementing the digital twins. So having implemented the digital twins, we move on to develop new control strategies to replace the existing control strategies on the building energy management systems of these case study sites. So to take you through these steps, I will take the case study we did on Queen Elizabeth Hospital, King's Lynn, as an example to discuss the results and these key steps. So, firstly, I will explain the technical details of the energy system and also the commercial arrangements. So, the on-site electricity network connects to UK Power Networks distribution grid, and at the moment there is an export capacity limit of 200 kilowatt to use when on-site electricity generation exceeds the demand. And the hot water network supplies the thermal demand in the network, and the energy system is also connected to the gas grid. And there are 2 CHP, combined heat and power generators in the site, and also there are 4 gas boilers to supply the heat demand. So in addition to these complex energy flows, there are complex commercial arrangements. For instance, there is a wind turbine on site which can generate up to 800 kilowatts and which is owned by Ecotricity. So these red arrows here shows the money flows in this specific case study site. So moving on to how we quantify through mathematical modeling the potential benefits that can be obtained by improving the operation or optimizing the operation. So in order to do this, what we did was we managed to collect large amount of time series historical data about the operation of this case study site. So that includes electricity import export, wind turbine output, CHP units operation data, electricity demand data, gas demand data, heat demand data, and also the electricity import export prices and the gas price. So we collected this data in half-hour granularity, and then what we did was for each of the time step, by building a mathematical model of the energy system, we ran optimization studies to identify for each and every time step what could be the best operation strategy or the optimal operation set points for the controllable energy assets. So then by comparing these outputs with the original operation, we could quantify the potential benefits. So we created a dashboard to show these data and also the potential benefits. So this just shows a screenshot of 1 week operation. So you can see the red line here shows the original operation, the cost, and the green line shows the optimal operation costs. So when we look at the full-time step for year 2020, we could see that compared to historical operational data, the optimization shows 13 to 14% of cost savings. But we need to keep in mind that these figures are highly dependent on the quality of the historical data. And then moving on to the second project. So we first started establishing digital twins of the case study multi-energy systems. So essentially the digital twin is a digital replica of the multi-energy system. So how we built this is we collect this historical operational data, and when there's possibility, we get real-time measurements from the building management systems of the case study sites. And also, in order to replicate the current control strategy of the building energy management systems, we studied the current control strategy and we developed the control strategy using a software code in our digital twin. So this digital twin allows us to test new rules, monitor changes in terms of carbon and cost savings. So like I said, this digital twin is computer model analog to a real world system. So let's see now how this real world system and the virtual system match to each other. So let's look at the real world system. So there are external conditions that impact the real world system, such as the day of the week, time of the day, and the ambient conditions. And also in addition to that, there's buildings and occupancy that is determining the electricity load, the site heat load, and the cooling load, etc. And based on that, the controllers in the building energy management systems decide which energy assets to switch on, switch off. And based on those control commands, the electricity and the thermal behavior of the system is defined. So in order to replicate this, what we did was the external conditions are now emulated or use the natural conditions to simulate these external conditions, and the building and occupancy to determine the site energy, electricity load and heat load, etc. We use the historical data plus trained machine learning models to give the electricity, heat, and cooling demand profiles. And like I said before, we first replicated the controller action or the controller logic of the existing building energy management system. And in this new project, what we are doing is we are basically trying to replace this control strategy. And how we test this is we develop a software code, and from the software code we give software logic to track the asset status, and then in our mathematical models we can run these new conditions or the new set points for the controllable energy assets and calculate the costs and carbon benefits. So moving on to some of the results. So based on the QEH case study, here I'm showing the electricity profiles of the real operational data and the digital twin data to show you how good approximation is a digital twin to give an idea about the real operation. So let me explain you the left-hand side figure first. So the negative side shows the electricity exports. So at the moment, there is a limit of 200 kilowatts of electricity exports. However, the actual operation most of the time limits it around 170. So after 170, it ramps down and do not export anymore. So we see from the actual operation, from the data, there are exports in this week. And then the blue and the orange color shows the CHP units generation. This one is blue color is the CHP1 electricity generation. On top of it stacked the CHP2 electricity generation, and on top of it is the wind turbine generation. And the dark orange color shows here the electricity imports from the grid. So if you look at the top line of this stack chart is the electricity demand of the site. So this is the real operational data, and after we implement the existing controls in our digital twin and pass all the other conditions, this is how the digital twin replicates the operational data for this specific week. So as you can see, it's a good match. So because of that, we can say we can use the digital twin to validate our new control algorithms. So now moving on to developing these improved control rules for the multi-energy systems. So the first step is to get the optimization results that which we use to quantify the potential benefits, and use those optimization results to identify patterns to decide the operation patterns for the controllable energy assets. And also, if you remember a previous slide I show you, there are other factors we need to consider, like the real-time weather, the real-time load changes and price changes, in order to really optimize the operation. So this new control algorithm should be able to respond to the real-time weather, load and price forecasts. And also we need to keep in mind that there are some other operational constraints, like the number of stop-starts for CHP generators or some other assets to maintain the lifetime of the energy assets. So these are the key things we considered, and in the end, we trialed these new control strategies on a hardware-in-the-loop testing environment, where we purchased few Schneider controllers and wrote our new control strategies into these controllers. So going into the details of this third step, so like I said before, at the moment, in the QEH energy system, the Queen Elizabeth energy system, the control strategy is based on a static rule set. So we do not want to improve the operation of this site by bringing in so many additional devices and additional controllers. So we want to try and improve the operation with minimal costs. So because of that, we broke down this improvement process into several steps. So the first one is to use the existing input parameters that the BMS is already using and write a new rule set to improve the control. So we don't get any additional inputs. So at the moment they're using electricity demand, heat demand, and the wind generation as the input parameters, and we use them as it is, but we write a better control algorithm. And the second one is we take additional inputs, such as the price variations, and write a new control rule set. And lastly, we take forecasts, day-ahead forecasts of all these parameters like electricity demand, heat, wind generation, and electricity prices, and we plan ahead for unscheduled shutdowns of the CHPs and optimize the operation of the energy system. So we write a new rule set for that. So these are the three sub steps to development of new control strategies. So now let's look at how from the optimization results we move on to derive a rule set that can be implemented in the building energy management systems. So let's first look at this table below. So how the optimization works is we pass for the optimization model number of variables such as the electricity demand, the heat demand, the wind generation, the electricity prices as in different combinations. So we try to cover the whole horizon of the actual operation in terms of these variables. And for different combinations of these variables, we run an optimization and get an optimal set of outputs for the controllable energy assets. For example, if the electricity demand is this much and the heat demand is this much and the wind generation and electricity prices are this much, the optimal gas boiler output should be this and optimal CHP electricity output should be this. So we got this kind of large data set. So having got that, now we need to make it a simplified rule set. So what we did was, by looking at the energy system, we thought the best, actually it is a heuristic approach, the best control strategy should be implemented for the CHP. So by looking at the CHP electricity output, we decided to define set of modes for the operation of the CHP unit. So now the whole optimization data set, we can categorize it into different set of modes. And based on the modes, we can then go into a machine learning algorithm to train this whole data set, train a model based on this whole data set to forecast the mode of operation for CHP units. So this is how we define the modes for CHP generation units. So we look at the electricity output given by the optimization, and if the electricity output is between certain values. If the electricity output is 0, that means both CHPs are off. If only one CHP is on and we are not exporting to the grid, the CHP electricity output is between these two values. So likewise, we defined 5 modes, and so that we could classify this whole data set into 5 classes. And then we used machine learning techniques. So classification, mainly some classification algorithms in machine learning to train a model. So in this specific study, we choose the decision trees because it has the advantage of being easy to be interpreted into a simple rule set. So we choose the decision tree approach. So using different predictor parameters, like I mentioned earlier, for different stages of the development, we train different decision trees and check their accuracies and complexities, and finally choose a decision tree and then convert it into software code, which is more like a if-else type rule. So this kind of rules are usually implemented in building energy management systems. So the other problem we had was how to manage the other operational constraints, such as the number of stop-starts for the CHP generators. This case study site was quite interesting because they had the wind turbine on site. So there was an issue in the practical operation that we identified from the energy manager, that there is a constraint for the CHP start-stops of number of 3 per day. However, when it is a very windy day, the CHP stop-starts happen, let's say, earlier in the day, and the CHP becomes not available for the following hours of the day, so which is not very efficient operation. So how we can improve it? So what we did was we used the forecast, the day ahead forecast, and plan ahead for these unplanned CHP shutdowns. So for example, here you can see the blue line shows the forecasted electricity demand. The green line shows the forecasted wind generation for the specific site. And the dotted line shows the net electricity demand, which means the difference between the electricity demand and the wind generation. Based on that, if we run our new control algorithm, we see that the CHP1 and CHP2 switch on and off more than 3 times per day, which is not ideal. So what we did was we looked at this day ahead and plan for the optimal schedule for the CHPs to be on and off under these wind conditions, but have the most useful power output from them. So we managed to implement this switching frequency control to our new algorithm. So this shows for the full data set for year 2020, which we had data from January to August, how the new addition for the algorithm managed to reduce the number of stop starts. And finally, I'm showing some results to show you how the new algorithm that we implemented performs. So this side again shows a very similar diagram to what I showed to you earlier. This is the original operation that we simulated on the digital twin. So you can see here the line of the stack chart shows the electricity demand, and electricity demand is met by the CHP1 generation, the CHP2 generation, the green color wind generation, and the dark orange color electricity imports. And there are electricity exports to the grid, which brings revenue to the on-site for the site. And this is the original operation, and this is the new operation. So you can see clear differences here. The new operation based on the new control set have significantly improved the amount of exports to the grid, which brings more revenue to the site. So that's how it brings more profit to the or reduce the energy bills of the energy system. And also you can see here the CHPs are not sharing the load in the original operation, but here the CHPs are sharing the load, and also the electricity imports from the grid has reduced largely. Here you can see a lot of electricity imports to supply the electricity demand, but with the new rules, it's less electricity imports from the grid, which means reduced electricity bills. However, that would compensate from the gas cost when the CHP is burning more gas. And then this one shows for this. So this one is for the winter week, and this figure shows for the summer week. In the summer week, it's slightly different. So the optimal operation implemented by the new rules compared to the original operation shows less exports. However, this is still cost optimal compared to the original one, because you see you don't have much imports from the grid. And when we look at how good is the new improved rule set compared to the theoretical optimization, which assumed the perfect foresight, you can see that there is a good match. The total amount of electricity generated by the two CHP units are very similar, and also the electricity exports to the grid are very similar, imports are similar. So you can say that the new algorithm has been able to implement what the optimization, the theoretical model said. So in a summary, finally summarizing the benefits of this improvement of the improved control rules. So the new control rules are able to reduce the utility bills. So we've done at the moment only for cost savings. We didn't do for the carbon savings yet. And we had recognized that there is a conflicting objective in both cost savings and carbon savings. However, if we look at the cost savings, we can see that increased revenue from electricity export and also reduce electricity imports and reduce gas boiler use, because the CHP units are running more and they are utilized more. So they're producing more heat. So there's less need for using the gas boilers to supply the heat. And also we've made some improvements for the number of stop starts that would impact eventually for the lifetime of the energy assets. And also we can say that this requires minimal hardware apart from an engineer to have go and having to replace the control strategy of existing rule set. And this is a simple schematic of how we set up the hardware software test bed. So we've purchased two Schneider controllers, and for these Schneider controllers we can log in and write a code like the code we developed as an nested if else rule set. So for this one we cannot really connect to the actual system. So what we did was we got the historical data and the data models to emulate the behavior of the actual system, and also we have the other forecast models to give the forecasts of the weather, energy, and the price signals, and then having the controllers running the new controls. This outputs us the optimal set points for the controllable energy assets. So we run this simulation models of the energy systems and pass it back to the system condition emulator. So this is the simple schematic of our test setup. So as a summary, key takeaways from this presentation, I hope, is that we understand that public sector has a great potential to lead the decarbonization agenda in the UK, but there are significant challenges remain, and also there is a need for user-friendly, accessible decision support tools to identify the improvement opportunities of public sector energy systems. And in order to do that, good quality energy data collection and analysis is very important. And also we identified that there is a gap between sophisticated academic research and simple analytical approaches to really apply them in the real world. So yeah, that is it from me today. Thank you very much. If you have any questions, I'm very happy to discuss those.